Yeah, so midterm 2 is on Thursday. I hope you've all seen the format of the exam. So there'll be one true-false question with justifications, and then there'd be 3 other questions: one on greedy, one on dynamic programming, and one on LP, max, min-max, you know, 2-person zero-sum games, duality. Let's see. So I think we were slightly loath to say this unless we knew it was absolutely true. But you should think of the LP and 0-person games question as being, you know, not entirely an algorithm design question. So it'll be somewhere between a short answer, conceptual question, maybe with a small hint of algorithm design in it. So that's what that will be like. Now, the other thing was, I think that many of you had asked what the relative rating of all the exams would be. So yeah, I'm not sure why. I think we had talked about it at some point, and we had decided it would be something like 20% for the first midterm, 25 for the second midterm, and 35 for the final. So is that correct, Abhishek? Is that what do you remember?
That's what I recall.
Yeah. Okay. So we'll confirm that, but that, to the best of my recollection, that's what it was: 20, 25, 35. Okay. So just for concreteness, in case it helps you feel better. Okay. So now let me go ahead and share my screen, and we'll get on with this lecture. Okay, so okay. Oops. Yeah. Okay. So here's my plan for today. So the plan is to do a brief sort of tying together of the last lecture. So what I'll do is, you know, in the last lecture I spoke about multiplicative weight updates. And I talked about zero-sum games. And I didn't have time to tie the two together. So that's what I'll do to begin with. And then, so just tying these two together, and then whatever time we have left, I'll do a little bit of review for the midterm. Okay. All right. So let me recall for you what the multiplicative weight updates look like. So in multiplicative weight updates, we have n experts. And we are going to play for t days. Okay, so, and then we have days going this way. So 1, 2, all the way up to t. And on day number t, if you follow the advice of the ith expert, then you suffer a loss of L sub. How did we denote it? Was it L sub I of t, or is that what was that what our notation was? You know, I don't completely remember. So let me see.
You definitely had the T as a superscript, but I don't remember about the I.
Okay, so yeah, maybe it was L sub I of t. It was like that, let's say. Okay, so let's say it was L sub I of t was the loss. And what we had was, you know, each of these losses, L sub I of t, was in the interval between 0 and 1. Okay. So now in multiplicative weights, what we did was, you know, we started off with weights on day 0. We started off with weights W sub I equal to 1. So we gave equal weights to all the experts, and then we picked a random expert to follow. And then on day 1, we saw the losses that each of the experts incurred. So maybe expert 1 incurred a loss of 0.1, expert 2 incurred, you know, was unlucky, incurred a loss of minus 0.9, expert 3, 0.5, maybe somebody here was very unlucky, had a loss of 1, somebody else had a loss of 0, maybe, and had a loss of 0.3. Okay. And we happened to pick one of these experts. Maybe we were somewhere in the middle of the road. We picked number 3, so we incurred a loss of 0.3. And then based on these numbers, you know, the losses each expert incurred, we updated the weights, and then we played again. And the next day, you know, maybe we decided the next day to go with that expert the next day. So this is the expert we went with. And now the losses the next day were completely arbitrary. So, you know, maybe it was 0.7. So we weren't that lucky. Maybe this person still had a bad streak. That one was doing well. This one reverted back to the mean. That one still did well. You know, whatever. So these are just arbitrary losses. And then on day 3, again, we chose who to go with, and maybe that was the expert we went with, and we just incurred losses. You know, we filled in these tables and so on, all the way through T. And then at the end of the day, we look at the loss of each expert. So then we look at the total loss incurred by each expert. And so if you look at the total loss, we'll just add up this entire row. And possibly this first expert, you know, over T days incurred a loss of T over 3. Maybe this second expert did pretty badly and, you know, got a loss of T minus 5. Maybe the third one actually did pretty well and the total loss was 10, etc., etc. You know, we go down the list and we see how much each of them loses at the end of the year. You know, so each of them has some loss. You know, this one maybe has a loss of 100 and so on. Okay, so now we look at the expert who in retrospect did the best. So this was our expert who did the best in retrospect. So we call that L star. Okay, if we only knew what was going to happen through the year, that's who we would have gone with. What did we actually do? Well, you know, what we did was we picked this and then that, and then we went through in some way, you know, we just picked a different expert each day, you know, according to our algorithm. And okay, so we actually we incurred so MWU loss was equal to L of T. Right? That's the loss we incurred. And then the theorem that we proved or we claimed was that the loss we incurred, is that how we denoted it was at most log n divided by epsilon plus 1 plus epsilon times L star, right? Where epsilon was the tuning parameter for our multiplicative weight updates algorithm. Okay. Is that okay? All right, so that was our algorithm. And what was our algorithm? Our algorithm was just, so what was MWU? You just tune the weights. You just let is equal to 1 minus epsilon to the L. Sorry, let me just see what notation I used last time, just to make sure that I'm not changing things on you. Okay, so W of okay, so I guess I just simplify the notation. So I'll just keep the simple notation that I used last time. So what I said was Wi of gets updated on each day to what it used to be times 1 minus epsilon to the power of the loss suffered by okay, so just for clarity, I should say in the last lecture I used the notation L sub I superscript T. This was, and now this time I'm calling it L sub I of T. Okay, so I just don't want to rewrite it. Okay, is that okay? So all we are doing is we just keep updating the weights. The more loss some expert suffers, the more we decrease that weight, and then we every day we just pick we then pick expert I with probability W sub I divided by summation of W sub J. Right? So we just pick the experts according to these weights. All right, so that's as far as experts go. Now let me try to connect this whole thing up to zero-sum games. Okay, so in a zero-sum game, you could imagine that the zero-sum game we are playing is given by the following matrix. Let's say this is Alice's Alice is playing against Bob. Alice has 3 possible moves, and Bob has 3 possible moves, and the payoffs for these 3 moves, we usually write it from the viewpoint of Alice. So however much Alice wins and Bob loses. So in this case, let's say that what Alice wins is between 0 and 1 always, and so Bob loses between 0 and 1 always. And so you could say that the payoff is something like this. It might be 0.2 here, 0 here, 1 there, 0.5, 0.6, 0.3, 0.9, 0.5, 0.2. Okay, so you're given given some game of this kind. So Bob's losses are between 0 and 1. Alice's gains are always between 0 and 1. And now we know that there's always a there's a strategy that Alice can use, which guarantees her that no matter what Bob does, she's guaranteed some amount. So she'll pick 1 with probability x1, 2 with probability x2, 3 with probability x3. And so now, and we are saying Bob plays in general with probability y1, y2, y3. That would be his strategy. And what we are claiming is that there's a best strategy that Alice has in terms of the best she can guarantee. So what she's going to do is she looks at so if we call this matrix M, so the payoff is X transpose MY, right? This is equal to the payoff. That's what we saw last time in our notation. And so what we said is, well, if Alice plays according to X and Bob plays according to Y, you can compute from this what's the expected gain that Alice makes and the expected loss that Bob makes. And now what's Bob trying to do? Well, Bob's trying to, from Bob's point of view, what he's trying to do is he's trying to minimize Y, the amount that he loses. And then what Alice is trying to do is pick the maximum over X. So this is the best she can do under the circumstances. Whereas the other possibility is that we think of it from the point of view of Bob going last, and then you have what Alice is trying to do is maximize over X, and Bob is trying to minimize over Y. And what we claim, this is the crucial thing. That's the min-max theorem. It says that these two strategies achieve exactly the same thing. So in other words, Alice can announce her strategy x1, x2, x3 if it is the min-max strategy, and she can go away and let just have her side be played that way. And then of course, once Alice announces her move according to whether she if it's picked according to probability x1, x2, x3, she whoever is playing on her behalf announces whether row 2 is played. Then once this player who is playing on Alice's behalf chooses from this probability distribution and says row 2 is being played, then of course Bob can optimize and say, well, I want to play column number 3. So it seems to be an advantage to go second, right? And similarly, if Bob announces his strategy saying, I'm going to pick according to y1, y2, y3. So y1 is half, quarter, quarter. And if he happens to pick column number 2, and he announces it, then whoever is playing on his behalf picks column number 2 from that distribution. Well, then Alice can now pick row number 2 to play because that's the best thing to do, right? Because she wants to maximize her winnings. And so it's a bit surprising that what we are saying is that there's a probability distribution that Alice can pick from, which she can just announce in advance and have somebody play on her behalf. Okay, so sorry, I sort of okay, so now let me sort of back up and restate what this min-max theorem is saying. What the min-max theorem is saying is, look, if you actually announce which row you're picking, then the column player has a distinct advantage. If you announce which column you're picking, then the row player has a distinct advantage. But if you announce in advance which, the probability distribution, x1, x2, x3, from which you're picking the rows, then you can set it up so that the column player has no advantage, even though they know exactly what strategy you're going to use, that exactly what the value of x1, x2, x3 is. You know, that x1 equal to 0.3, x2 equal to 0.4, x3 equal to 0.3. Announcing this, you know, you can pick the optimal strategy and you can announce it in advance, and Bob doesn't get an advantage from knowing that. And similarly, if Bob announces his optimal strategy, Alice doesn't get an advantage from that. Okay, that's what this min-max theorem is saying. So now, now what, you know, the interesting thing here, the connection between multiplicative weight updates and this and zero-sum games is that you can show using multiplicative weight updates that in fact this equality holds. So you can prove this duality theorem. Moreover, you can even use it to efficiently come up with strategies for Alice and Bob which are nearly optimal. Okay, so that's the interesting thing about the connection between multiplicative updates and zero-sum games. Okay, so let me, before talking about that, you know, I'll just talk about that very briefly. I'll touch upon that. I'll give you just a sketch of how that goes, and then you can read it up in the notes if you're really interested. You know, so it's sort of slightly advanced, so I don't want to belabor it too much, but I do want to give you a spirit of it because it's such a nice thing. Okay, so so I'll stop here for a few questions, and then I'll spend 5 minutes just talking about how this is done.
Okay, so a good question just came up in the chat saying if Alice announces a suboptimal strategy and Bob can still announce a different strategy to take advantage of it. I guess the question is, yeah, okay, the question is, can Bob still announce a different strategy to take advantage of that and improve Alice's payoff? I don't know, maybe somebody can unmute themselves and explain what they're saying. So, yeah. Okay, so I'll try to rephrase this again. So if Alice plays optimally and Bob does not, can Alice have a higher payoff than expected? And another way of saying that question is, that somebody asked right after, is if Alice announces a suboptimal strategy, then can Bob still announce a different strategy to take advantage of it? I think that's what the question is. Yeah.
Yes, that's right. So, you know, so here's the answer to the two questions. Let's suppose that Alice announces a suboptimal strategy, and Bob announces his optimal strategy. You know, Bob sticks with the optimal strategy. Well, then Bob could do better, right? Bob might do better than this value of the game because Alice is playing suboptimally. But you could also ask the question, well, if Alice is playing suboptimally, you know, could Bob do better than playing his optimal strategy? The answer is absolutely yes. You know, if Alice is going to be suboptimal, then it might pay for Bob to also be suboptimal. So for example, if Alice decides to, instead of playing her optimal strategy, x1, x2, x3, she just decides she likes the third row, and she'll always play 3, okay, for some reason. Okay, so now once she plays suboptimally, Bob could continue to play his optimal strategy, whatever y1, y2, y3 are. And so he'll get some combination of 0.9, 0.5, and 0.2. But he could also play suboptimally in general, but he could just, since he knows Alice is always playing row number 3, he could always play column number 2 so that he minimizes her gain, right? And so if you know your opponent's strategy and it's suboptimal, then you might be able to do better than your optimal strategy is sort of a defensive strategy. It's sort of saying, look, if I'm playing against somebody really good, then, you know, if I deviate from this strategy, they'll really punish me for that. But if I happen to know I'm not playing against somebody who can punish me, I'll sort of take some chances and do something where if I was playing against somebody who was very strategic, I'd really suffer huge losses. But I'm going to do this because this person is just not going to exploit that. Does that make sense?
I think that makes sense, but maybe another question we should address, which also came up in the Piazza thread, is a little bit simpler, and it's about the circular definition of how you're optimizing for both Alice and Bob. So since they're not announcing their distributions beforehand and playing simultaneously, I don't know if you're going to go over the setup of the dual and the primal LP, but it's a clarifying question on how you can decide the optimal strategy for Alice and capture the rationality of Bob.
I'm not sure I completely understood that. Paraphrase in one sentence, or?
We have somebody who is raising their hand, and I think it might be the same person who asked it on Piazza. So Li Cheng, I think. Yeah.
Yeah, that's me. So basically, it seems like over here we have two situations. Either Alice announces the distribution first, or Bob announces the distribution first. But I'm wondering, like, what if both Alice and Bob didn't announce the distribution beforehand and they just play? So like we play rock, paper, scissors, shoot. And before we play, we will not tell each other the distribution I'll play. In that case, how can I make an optimal strategy?
Well, I think I think this min-max strategy is sort of telling you how to play, right? You sort of say, look, if the other person knows how, that the optimal play is to do this, they would, I mean, if you want to be pretty secure in what you're doing, you would use, your optimal strategy like this. And then, no matter what the other person does, they cannot make you do any worse than, what this payoff is. On the other hand, if they play with their optimal strategy, you cannot actually gain any more than this. So, in that sense, that's a good worry-free strategy. Now, of course, maybe you have some other information on the side about how this other person's going to play, and then you might use that to punish, to do better. But then they might know that you have this information about them and that you're going to do this. So they do something to exploit this strategy and so on, So then of course we are in some, then we have no way of analyzing that, right? But the fact that in this situation where it seemed like there was no way to understand how you could play, that there's this pair of strategies which are optimal with respect to each other, in the sense that you play each other and you're in an equilibrium. If either of you deviates from the strategy, you're going to do worse, right? So it's in an equilibrium. It's like the best. It's like the two are in an equilibrium. They have the property that as long as if both of you play this strategy, you have a certain payoff. And then whichever if only one of us deviates from this pair of strategies, then whoever deviates from it is going to hurt themselves. So because of this, the expectation is that's how we'll play. Does that make sense?
So does that mean, like in our example in lecture on last Thursday, the X0 and the distribution, the value of distribution is always announced beforehand, and then the Bob can just deterministically choose a move, or like decide what he will play. But if they don't announce the distribution beforehand, then we just replace the value, the exact value, with the variable x0 and x1, and Bob, instead of coming up with a strategy of I will play this move.
I'm sorry, this is too long. I cannot understand what you're saying, and maybe it's not also good for the class. So can you ask me later?
Yeah, sure.
Okay, thank you. Okay, so let me move on. I'm going to move on and just do a very short I'm just going to say something very short about how one might use this to how one might use multiplicative weight updates to figure out the best strategy. Okay, so what do we do? So say that this matrix that we are given this matrix is let's say m by m. This is our matrix for the payoffs. So now what do? Well, we let the column players, these are the ones, we let them be the experts. So these column strategies, 1, 2 through m, these are the experts. Okay, each of them is going to suffer a loss. All right, so what we are going to do is, and these row things. So we are going to play the experts game, against these experts, and so we start off with x1 through xn on day 0. So on day 0, we just on day number t, that's going to be our probability distribution on day number t. Okay, so here we are playing multiplicative weight updates, and basically we have a probability x1 of t through x sub m of t. This is on day number t. And we just go ahead and, so how are we going to play this? Well, just like multiplicative weight updates, so x sub 1 on day 0 or on day 1 is equal to x sub m on day 1. So on the first day, all these are equal, so it's 1 over m. So that's what Alice plays, that's her distribution. And then we'll just let Bob play his best response. Okay. And then we just, so that's x on day 1. X on day 2 is something else. It's some other distribution according to multiplicative weights, according to the loss each one suffered. And Alice plays this new distribution. Bob plays best response again. Okay, so anytime Alice says this is the distribution I'm playing, Bob can just say, okay, this is my best response to it. And so you just go ahead and do this for t days. And Bob's response we'll call y of 1, y of 2, y of t. And then what we'll claim is that if we look at the average of all these probability distributions that Alice plays, and the average of all these probability distributions that Bob plays. Okay, then this turns out to be you know, these two strategies are almost optimal strategies playing against each other. So these are the two strategies which almost achieve this, this optimal bound. And so the exact claim is that that if we use t equal to log n over epsilon squared, then you know, then the gain that Alice gets by playing X is within 2 epsilon of the loss that Bob suffers if he plays Y. Okay, so if we call this X, if we call this distribution Y, then X versus Y are within 2 times epsilon of optima. Okay, and the proof sort of you know, maybe I shouldn't go over the proof just because it's you know, I think that at this point I can, okay, so I could either do a sketch of the proof or I could do a little bit of a review for the midterm, whichever you prefer. So the proof is going to be, you know, there's a very nice, very simple proof that you can read about if you're really interested. It's not very long. It's just a few lines, and the basic idea of it is that you know, the basic idea is that, you know, you end up writing some sort of an inequality which says L star, you know, sort of the amount that Alice wins through all of these T rounds, or the amount that Bob loses in all of these T rounds is, you know, is an upper bound on the total amount that you know, that Alice would win if you took this average strategy X and you asked Bob to play his optimal move against it, and that further is an upper bound on the, so this is best response to X. That's Alice's best response to X. That's Bob's best response to Y. And then since we are talking about X and Y as the average, so I should also take L star divided by T. So it's the average loss that Bob suffers, or Alice, the average gain that Alice gets. And then what we, you know, the only other ingredient, so I'm going over this very fast because I'm just giving you a sketch so that if you want to read about it, you know, you can orient yourself. So the basic thing that now we assert is that, you know, sorry, this was not this was the loss suffered by multiplicative weights. So this I call not L star but L of T, right? Whereas this would be equal to L star divided by T. And so now what we can say is that the distance between these two, you know, by the multiplicative weight update theorem, would be, you know, so we know that you know, that these are, we know how to bound the distance between these in terms of log n over epsilon, and that's how we that's how it's bounded. So this is what you bound by the multiplicative weight updates bound from the theorem, and that tells you that you can say, well, the best response to Alice's strategy versus the best response to Bob's strategy, they are within 2 epsilon of each other because R of y and this is within 2 epsilon of each other. So we are bounding these 2 quantities, between 2 numbers which are 2 epsilon apart. So we've said that they instead are also 2 epsilon apart. Okay, so that's sort of a very very rough picture. It would take probably more time to go over it, but my feeling was maybe it's easier for you to read through some notes about it, and then if need be, I could do a little video about it and post it, if there's interest. So let me stop here for questions, and then we can.
Yeah, there's one question in the chat. Basically, it says, "How do we choose a strategy if we don't know opponent's strategy? But we know that
what?
So how do we choose a strategy if we don't know the opponent's strategy, but we know that
what strategy?
The opponent's strategy.
How do we choose a strategy?
But we know that the opponent isn't going to play optimally every time.
Mm-hmm.
And there were some more questions about if multiplicative weights algorithm helps with that.
Okay, so here you see what multiplicative weights is doing. So what we are saying is, look, we want to figure out what this, we want to try to converge towards an optimal strategy. So how do we do it? We start with a uniform strategy, right? So everything is equal. And then we let the, and then we let, let each of the, we always play the best column against it, right? And then we just keep doing this time after time, and we see how we do, and we keep adapting the, we keep adapting our probability distribution of our play according to this multiplicative weight strategy. Okay, so that's what we're doing. So we see, we are playing a certain strategy, and then what we do is we, depending upon how each of our moves does, we make it either more likely or less likely, and we just keep adapting it. And the claim is that if we do this for a number of days, then, and if our opponent is really playing well, then our average strategy then we are going to be converging towards the optimal strategy. And we are converging towards the optimal strategy in the sense, not that our strategy needs to converge day-wise, but if you look at the cumulative strategy we have over the last so many days, then that's going to converge. The average strategy over the last so many days, it's going to converge. And what's it going to converge towards? It's going to converge towards the optimal strategy that we can play. Right, so that's the main theorem. There's also a really nice next step that you can go to, where instead of Alice playing this multiplicative weights and Bob playing best response, you would have Alice and Bob both playing multiplicative weights against each other. So they both start from the uniform distribution, they both play multiplicative weights against each other, and then essentially in roughly the same time, maybe twice as much time, something like that, what you can show is that both strategies converge towards optimal strategies. Okay, so you don't have to even play best response. All you do is you start adapting to each other, right? And this is something that's algorithmically very significant. You know, the fact that you're trying to find these optimal points, and the way you do it is you just play multiplicative weights. You just try to learn from how you did so far, right? By keeping track of how each of these different moves you're making works. And your opponent is doing the same thing. They're also trying to learn from playing you. And the interesting thing is each of you sort of is just blindly doing that. You're just looking at how you do against this opponent. And your opponent is training you to do well, and you're training your opponent to do well. And by the time you do this for some number of steps, which is not very large, you're actually both doing pretty well against each other, and you actually found that optimal pair of optimal strategies, or very close to it. So this is something that's really significant, and it gives this very general way of thinking about algorithms, where to design an algorithm to do well in a certain situation, what you do is you set up a competition between two subroutines. You know, they are playing each other. And if you set up the competition right, then the two subroutines are going to train each other to actually solve the problem pretty close to optimally. Right? So that's the algorithm that that's where this entire philosophy is leading us towards. Okay, it's a little bit beyond the scope of this course, but if you were to take 270, you would see it being actually instantiated there. So you would see both multiplicative weights and zero-sum games. And then you would see how to actually use this philosophy to design algorithms for solving interesting problems, where you can think of the algorithms as training each other, you know, two different subroutines that are training each other to do something. And in the process, they both learn and they both get close to optimal.
Professor?
Yes.
You write t equals log n over epsilon squared.
Mm-hmm.
Where does the n come from in this case?
Oh, sorry, it's m.
Okay, thank you.
Thank you. Yeah, it's the number of players. It's the size of the matrix.
Okay, so we have one follow-up question on what you were just discussing, and then a couple of people are eager to get to review. So the last follow-up question is, will those two strategies, if playing adversarially with multiplicative weight updates, will they converge to some kind of min-max equilibrium solution?
Yes. Yeah. So they'll you know, in the limit they'll converge to the min-max solution, but over a finite period of time they'll sort of achieve weak duality, but weak duality to within epsilon, and you can tune the epsilon to be as small as you want.
And then if this is a good time to switch to review, since we have only 30 minutes left.
Okay, let's switch to
we have one request from Piazza, but we also haven't polled people for what they want to be reviewed. So if people want to drop things in the, I don't know if you have a specific plan, then you should go with that. But I was just going to suggest.
Well, I was going to go through a question each for LP, Greedy, and DP. But how about if I start on that, and if people don't like it, then we can switch to what they'd like to do. But let me try to do these, and or you know, I thought these are nice questions, and they might illustrate something. So.
Okay, perfect. Yeah.
Okay, so let's start with LP. Okay, so let me do an example of an LP. So here's a question that you might imagine that you're faced with, you know, in terms of midterm review. So you're trying your best to maximize your score on the midterm, and maybe there are 3 different strategies that you could follow. One is you know, so you have 3 strategies. You could just study, and you know, let's say S is the number of hours you put into just studying. H is you do any homeworks that you haven't done already, or maybe you do the most recent homework. And let's say R is another strategy, which is to review homework solutions. So what does it mean to review homework solutions? It means the solutions are released right after you turn in your solutions, and so what you do is you go back and look at the actual solutions, regardless of whether you think you got the answer correct or not. You go back and look at the solution that's been released, and you sort of see, well, does that solution help you simplify in your mind what the question was asking? And okay, so why would you do that? Because the point of what we are doing in this class right now is that you learn how to think about, how do you design an algorithm, and how do you understand the main point of it? How do you understand the main argument for correctness? Right? These are two of the most important things. So let's say you actually solved a problem correctly on the homework, but it took you, 2 hours to figure it out. And now you look at the solutions, and let's say that particular solution happened to be particularly nicely written, and it was only, the write-up was only 3 lines. Okay, both in terms of, it was 2 lines of describing the actual algorithm, and then it was another 3-4 lines of describing the main idea of why it was true. And so you look at it, and you might have one of 2 reactions. You might think, oh my goodness, this is discouraging. Or you might think to yourself, actually, if I look at it and if I understand this might actually help me understand how to, how I'd have thought about this algorithm in the first place. Maybe instead of going around like this, I could have gone directly. And now that I understand the main idea really well, because it's given to me really clearly, this should help me understand both how, what it means to justify this algorithm, as well as how to find it. So now you look at, well, how much benefit you get from these strategies, and you realize that that your final score, or somehow the benefit, however we measure it, looks something like 5 times R plus 1.5 times H plus S. Okay. I don't know what the relative weights of H and S should be, but I feel that this, if you put in this time to review the solutions, that's a really good strategy in terms of understanding how to do well. But then there are some constraints on this. You can't really do this review for too long, so maybe you can do it for at most 2 hours, and maybe that's even a bit of an overestimate, because you really do want to do it, but you want to do it in a nice focused way. Maybe H is less than or equal to 6, and maybe R plus H plus S is less than or equal to 25. Okay. And then you have R comma H comma S is greater than or equal to 0. Okay, so these are your inequalities. And now you might think, okay, so how would you write the dual of this? Well, to write the dual of this, what you're trying to do, remember, you're trying to say, multiply each of these inequalities by a variable, say x, y, z. Okay, and now since we want to multiply the inequalities and we don't want the inequalities to flip, we'd have x, y, z greater than or equal to 0. And now what we want from all this is we want some constraints saying that, when we add all this together, what we'll get is R times, when we add these inequalities together, we'll get R times x plus z and H times y plus z and S times Z. And we want to say, we want to say, well, this is a constraint on how big this objective function can be. And so since we want a constraint on how big this objective function can be, we want this to be greater than or equal to 5, this to be greater than or equal to 1.5, and S or Z to be greater than or equal to 1. So we want X plus Z greater than or equal to 5, Y plus Z greater than or equal to 1.5, and Z greater than or equal to 1, right? Now, in all of this, the reason we put greater than or equal to is because we know that X, Y, that R, H, and S are non-negative. So if we put an upper bound on 5 times R, if we actually put an upper bound on 6 times R, it's even better. So the solution certainly cannot be better than that, right? And now what we want to do is minimize the upper bound we get. So the right-hand side we'll get over here. So we'll get this is less than or equal to 2x plus 6y plus 25z, right? So I'm just adding these inequalities together. So I'm just saying multiply these inequalities by x, y, and z, add them together, and you get this inequality. So what I want to do is minimize this upper bound, which is 2x plus 6y plus 25z. Okay, so this was how you write out this dual program in the case that this program was in standard form. But now, what if a program is not in standard form? What if you had an inequality which said R plus H greater than or equal to 3? The inequality is going the wrong way. Well, you can always flip it by multiplying by -1, and you get minus R minus H less than or equal to -3. Okay. What if you have a variable t which is less than or equal to 0? What would you do then? Well, you would then introduce a new variable u equal to minus t, right? And now u is greater than or equal to 0. So you just do the substitution. What if you had some other variable z for which you don't know whether it's greater than or less than 0? It's just unconstrained. Well, then what you would do is you just write z equal to z plus minus z minus. So you just introduce 2 new variables, which we'll call z plus and z minus. If you want, you could call them something else. You could call them u and v. And you just put in the constraint z plus greater than or equal to 0 and z minus greater than or equal to 0. Okay. So you can always take any LP and put it in this form, and then you can do the 2. So I should say very briefly that one of the reasons I actually went through this was to I was actually quite serious about how you should study for this particular course in general. If you're so in the surveys, many of you said that you spend up to 6-8 hours on the homework, and I was thinking about it. So if you were to instead spend an additional 1 hour going over the solutions as soon as they come out, and think about go over this and with the view to thinking, could you have done it much more easily? And if you follow it, rethink through it while it's fresh in your mind, that would help you a lot. But if you don't want to spend any more time, let's say if one of you is spending 8 hours on the homework, and you decide, no matter what, you're just going to stop at 7 hours and spend 1 hour really reviewing these solutions, I think you would do much better in the long run in terms of how you do. So just a piece of advice about how to go about studying for this exam. You know, it's much more. And I should say one other thing. You can also be confident that when you're writing your midterm, you know, that we are not going to be very nitpicky about, you know, did you miss, you know, did you miswrite something? Did you miss saying something? You know, that's not our purpose at all. So what we are really looking for is, did you have the main idea? Did you design a good algorithm? You know, did you really understand the main idea about why it's correct or how one analyzes it? That's what we are interested in, and we are not going to be very nitpicky about, well, did you dot the i's, did you cross the t's, right? And so that might also inform your strategy about how to study for the midterm. Okay, so that's the LP question. I'm going to just go on because we don't have that much time. So let me just talk quickly about a greedy question. So let's say it's a very simple one, but I think it illustrates some of the ideas. So let's say that that we are given a bunch of numbers, and let's say, you know, they could be rational numbers, or, you know, for our purposes, as far as we are concerned, they could even be real numbers. So, you know, and let's just think of them as being, you know, sitting on the number line. And what we have to do is we have to cover them using unit intervals and the minimum number of unit intervals. So for example, you know, you know, if you were being greedy, you might say, okay, let me look at the largest number that I could cover with a single unit interval. So maybe there are lots of points over here, so I could take a unit interval like that. And then I could say, well, what's the other most dense place I could pick? And well, that's a unit interval that contains these points. And then, of course, that's another dense interval, and maybe that's the next one, that's the next one, that's the next one, that's the next one, and that's the next one. Right? So we want to, given R1 to Rn, find minimum number of unit intervals that contain O. Okay. So now, how should you know, you can think of many criteria by which you could do a greedy solution. I claim that there's a nice one to think about. You know, if you think about how I went through this example, you'd realize that, well, when I picked these 3 points, it seemed like a pity, because then there was this isolated point sitting here, and then I had to devote an entire unit interval to it by itself. That seemed a bit wasteful. So a different way to do this problem is, what you could do is you could start from the left, and you could say, let me take a unit interval from the left. I've got to cover this point anyway. So let me just go ahead and find a unit interval and let it cover as much as possible. And then I throw those points out, and then I repeat. Okay, so start at leftmost point. Okay, so call that L, and you look at the interval L, L plus 1, and then throw out all points in this interval. And then repeat. Okay, so I claim that you know, that always finds the optimal number of intervals. Okay, so now, how would you show that it's optimal? So here's the idea. You know, the idea is, so the main idea is via an exchange argument. So I'll show you the exchange argument in two different ways, right? So the first way is you say, okay, let's assume for contradiction that greedy is not optimal. Okay. So let's say that the greedy solution looked like this. And let's say you had some other solution which you felt was better. Okay, so here's a better solution. Okay, so you have some better solution which looks like this. So I don't know what it looks like. Maybe it looked like that, but then it did something else. Maybe it picked these and then picked picked these, but then it did this and then it did that, so on, right? So it okay. So now what we are going to do is walk. Okay, so here's what our proof does. What we do is walk from left to right and find first difference. Okay, so in other words, what we are saying is, look, if you look at this interval, it's the same. The blue and the red interval are the same. Okay, so here's something where maybe the red interval doesn't look quite like the blue interval. So now what we do is we claim, look, so maybe this red interval went too far to the left. Who knows? It did something. So now what we do is we say, look, so far everything looked the same. Now, if I take whatever this red interval was and substitute it with the blue interval, so if I take my red solution and I cross out this interval and put in the blue interval, it's still going to be a solution. So you find the first difference and you substitute red interval with next blue one. So I claim that this is going to do at least as well. And why is that? Well, because the blue interval takes the next point that is uncovered, it's got to cover it, and then it goes as far to the right as possible. And so the red interval cannot do any better in terms of covering this point plus everything else that it does, right? So that just by geometry. And therefore now we have a solution which is slightly closer to the blue solution, and it's also better than it, right? So we started for a contradiction. The red solution was better. Now we found one which is equally good as the red solution, but it looks closer to the blue solution. So we just keep doing this over and over again. So now we keep doing this. And until we end up with the conclusion that in fact greedy was, we end up with the blue solution. So we achieve a contradiction. So you could say, well, what kind of proof is this? You gave me an algorithm, not a proof. So to convert this into a proof, what you would say is, instead you would say, assume for contradiction that it's not optimal. So then there must be a better solution. And among these, pick one with maximum overlap with greedy. And by maximum overlap, I mean, the first j intervals are the same. And you maximize j such that the first j intervals are the same. Okay, so now under this condition, I look at the red solution and compare to the blue solution, and I say, look at the first point where they differ. And you substitute the red interval with the blue interval, you get something which is as good, or at least as good. Therefore, contradiction. This was not the best solution, a better solution which had the maximum overlap. I showed you something which had even more overlap. Therefore, contradiction. Therefore, greedy was optimal. Okay, is this clear? So is it clear that at the heart of this exchange argument, there's an algorithm which says, I can move from any solution that you have, which you claim to be better, towards the greedy, and I'm only doing better, right? But then you convert it into a proof by saying, well, I only have to show you that that I can do one step of it, and already you will grant me that greedy was optimal. Okay. Okay, so I know I'm rushing through these a little bit, but that's because we don't have so much time left. So let me just okay. So the next one is dynamic programming. Oops. Oh no, what did I do? Oops. Okay, dynamic programming. So let's do this. So dynamic programming is basically a matter of writing a recurrence relation and understanding which solutions you remember, and in which order you remember the solution, so that you can solve the next one. So the subproblems. Okay, so let's see an example. So let's say that you're given three binary strings. A, B, and C, and you want to figure out, can you interleave A and B to get C? Right? So for example, if C was 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, and this was C, and A was, well, let's pull it apart. Maybe A was 1, 0, 1, 0, 1, 0, and B was 0, 1, 0, 1. Okay, so then you can see that, in fact, you can do this interleaving because A looked like this. Okay, and then B is this, right? And you can see that you're just interleaving. You start with 1, 0, and then you interleave a bit of 0, 1, and then you go back to 1, 0, 1, and then you put a bit of a 0 from here, and then you put 0 from there, and then you put 1. Right, so you're able to interleave them. Okay, So is it clear to everybody that this should be solvable by dynamic programming? Just take a look at it and, think about it and see if you, feel free to use the chat to say whether you feel that it's clearly one, or you're not sure how you would see it as such. So here, is everybody clear about the problem? Yeah. Okay. So here's a way that you might think about it. Or you might say, look, if I want to know whether C is an interleaving of A and B, another way of asking the question is, well, maybe I just want to know, if I look at an initial part of C, is that an interleaving of A and B, right? And so you might make up a subproblem where you say, well, is this really an interleaving? Yes, actually it is, because I can take 1, 0, and then 1, 0, this part of A. So I could take, oops. I would take this first part of A and 1, 0, 1, 0, and then I'd take this first part of B, and if I interleave them, I would get this first part of C. So, well, that's your subproblem then. So what you would do is make up a subproblem. I've forgotten the notation these days of what one does. Let's say S of I j is true if the first A of 1 through I and B of 1 through j can be interleaved to get C of 1 through I plus j, right? And now once you write it out, the rest of the dynamic program writes itself, as long as you can write out right? As long as you can right? So if you want to know, well, what about S of I j plus 1? Or you want to write out S of ij in terms of smaller values. So you want to know if S of ij is true. Well, it's true if either S of I j minus 1 is true and B of j is equal to C of I plus j, or if S of I minus 1 j is true and A of I equal to C of I plus j. Right. So now, now that we wrote it out, we're just saying, look, how do we know that these two match up with this? Well, one of these has to be one of this last character has to match up with either the last character of A, or it has to match up with the last character of B. If it matches up with the last character of A, then once you remove it from contention, then you have only I minus 1 characters left on the A side. You still have j characters left on the B side, and they must match the string up to the last character that we are seeing so far. That's right. So that's your subproblem S of I minus 1j, right? And then, of course, the only thing other thing you have to do is figure out how to get started and in which order to fill in the table. But that's sort of easy in this case, I think. So let me stop here for questions because I feel that we are exactly at 5 o'clock. And, I can also stop sharing this screen so that I can see you if you're, so if there are questions that require me to keep the screen, just let me know. Otherwise, I'll stop sharing.
We have a question about the optimality proof for the unit interval greedy problem.
Okay.
But I don't know if I should jump back to that or not first. It's asking, in this proof, do we assume that the optimal solution uses fewer intervals than the greedy solution? And if so, then by the swapping argument, you're swapping intervals from the optimal and greedy solution. So after swapping, wouldn't the optimal solution still have fewer intervals?
Yes, so that, by that point, we'd be at either we'd be at a contradiction early on, or we'd be saying, look, it was, the solutions were the same all the way up to the end, where the red solution ended, but the blue solution keeps going on, the greedy solution keeps going on. But how could it be, if you have this sort of a, you had the red solution looking like this. So remember, we've gone through the whole thing and we've tried to make them as equal as possible. And so all the intervals look the same right up to the end, but greedy keeps going on. So now there's a contradiction, because the reason greedy kept going on is because there must have been points in here that it wanted to cover, but your red solution didn't cover them. So that's a contradiction too, because it was supposed to be an honest to goodness solution, which means it should have covered these points, but it didn't. Right? We are sort of forcing this pretend better solution into a corner, right? By saying, look, we are going to start looking like you more and more in the initial segments, and somewhere something is going to break down, right? Either this solution was supposed to be equal as far as it could, and so we'll show that it'll be the same, one more step. And here we could either say, well, it must be the same one more step because it was a solution, so it must have covered these points. So it couldn't have ended here. Okay.
Gotcha. All right, we have one hand raised from Kentaro.
Professor, I was wondering, for the dynamic programming problem, would the base case just be S of 0j is false and S of I0 is false?
I would say maybe the base case could be S of 0, 0 equal to true, and then you just work your way up from there.
And also, are we allowed to just return like Boolean values by just doing like ands and ors?
Well, it depends upon what the question asks, right? So this just asks, is it possible to interleave? It may be that you're actually asked, how do you interleave? In which case you have to trace your way back. But that's all easy, right? So it's just back pointers and saying, which choice did you use? Did you in this step, did you use that or did you use that? Right?
Okay. Yeah, thank you.
Oh, we have a logistical question about adding DP solution formats to the cheat sheet. And yeah, the answer is the policy for cheat sheets is you use the given cheat sheet. I don't know if there are any other questions about the problems.
If you have a suggestion, then just write a post in Piazza with your suggestion. Maybe we will put it in the cheat sheet.
Yeah, we could still revise it. If there are no questions, I'd love to hear feedback on, you know, on what I was saying was a good
Study strategy?
Yeah, good study strategy. So I'd like to know whether it's helpful, whether it was news to you, whether you're already doing it, and you know it was obvious all along, and I shouldn't even have bothered. You know, so I'd love to hear what your feedback on that is. Maybe I should make it easier for those who are still there. You know, yes, if it was useful. No, if it wasn't. At least at that level.
Oh, we have a hand raised from Animish. Also, let me know if I'm saying your name wrong.
This idea of emphasizing homework problem review was rather new to me. As far as my understanding was, the best strategy for studying was always doing practice exams. So I was very interested to hear that, and I wasn't quite sure if you were entirely serious about that either.
Oh, I was completely serious. Yeah, you know, so I think that so let me try to elaborate on it a little bit. You know, so the homework problems are problems where you spend a significant, as far as I can tell you, you spend a significant amount of time grappling with those problems. So you've actually spent time thinking about them, getting to know them, and so from my point of view, that's a real opportunity for you to now see how to do them. You know, so let's say that you did the homework problem, you got it perfectly right. You know, so you have a solution which is completely correct. Even then, if you actually read up the homework solution, and if it happens to be written in a particularly nice way, so that you know, so that even though you had the right solution and you had a correct analysis of it, maybe it wasn't quite as simple as the one that's been presented. And when you look at it, perhaps it'll help you understand. You know, so it's like, you know, it's like getting from point A to point B, wherever you started from, to the solution, right? You took some path to get there, and now, if the homework solutions that are released, you know, give you a shorter path or an easier path, then you can ask yourself, okay, well, could I have thought of that, you know, or let me try to actually make this other path my own, so that the next time I see a question like this, you know, instead of wandering around like that on the longer path, I'll just, you know, it'll just be easy for me, you know, it'll just be a piece of cake just to get from here to there. So, and then if it was a matter of how do you justify the solution, again, if it was a much easier justification, so that you can see for yourself, oh, it was just this simple idea, you know, I could have written it in 2 lines instead of taking a page. Well, then it's easier to think with those simpler ideas, right? And one of the points of this course is that simple ideas are great. You know, we love simple ideas. You know, what this means is that in your exam, if you write out a solution and it's simple and it's correct, you know, we'll rejoice, and you don't have to write a lot to get full points on a question in the exam. You just have to be right.
Thank you. I think that sort of like active reading strategy you suggested it's far more informative than like my sort of just skimming the solutions that I was thinking of. So thank you for that.
Yeah. Yeah, that's great.
Yeah, someone in the chat says that that they're surprised you didn't include practice exams. but
Yeah, that so I'm not sure. Can you pass that for me a little bit more? So include practice exams in what?
in the studying strategy, one of the studying strategies.
You know, I thought I was, when I said you mean in the linear program, S included every kind of other study strategy from my viewpoint. It was either studying the concepts or doing practice, studying practice exams. I'm not sure how to assign weights to those. To me, all those are good strategies to follow. It's just that it seems to me that there's this one strategy which, to my mind, has a very high payoff, and that's what I was trying to emphasize. Okay, I should also say that this is there are individual variations in how people learn. So obviously, if it doesn't work for you, it doesn't work for you. But I would say that it's a really good idea to try it and see how it works, and try it meaning try to make it work, and get some, if it's not working, get some help or get some feedback. And if it still doesn't work, it's completely fine. Not everybody has to do things the same way. Right? But I think a lot of you would benefit from it. That's my feeling.
There's this one question that came up in the chat or Piazza or something during lecture that I didn't bring up because I didn't think it would be good to talk about at the time, but somebody asked if all intuitive LP setups have an intuitive dual. And I wasn't sure how to answer it. Other than that, there is some intuition behind how the dual variables and the objective function corresponds to each constraint.
Yeah. So
linear algebra is kind of intuitive, but
yeah. Sorry, go ahead.
No, go ahead. Sorry. Yeah.
So let me answer it in this way. There are often when you write out these constraints and you look at the dual variables, economists love these dual linear programs because the dual variables correspond often to prices. And so it turns out that these dual LPs often have a very nice interpretation. And here's one thing that happens more often than you would think is true, and more often than initially you might hope. You might wish for, which is you write out the LP, you write out the dual, you write out the interpretation of the dual, and it's laborious work to do that. And then at the end of the day, you say to and then you come up with this algorithm with these dueling subroutines, and then you simplify it all down, and then you realize it's actually a very interesting, simple, natural algorithm. And shouldn't you have thought about it without actually going through the exercise of writing down the LP, writing down the dual, doing these interpretations, simplifications, and so on? Turns out, I don't know, somehow it all seems really nice in retrospect, and the obvious way of doing things, except it wasn't obvious when you started off, and you have to go through this formalism and take duals and so on. So that happens more often than one would like.
Yeah, I think it's a good question.
I think there's a good example that you gave with how to study, give a meaningful meaning for these X, Y, and Z variables.
What
variables?
Oh my goodness! Oh.
What do they capture?
I don't know. That's a good question. I really don't know. Do you have a guess?
Maybe I don't know. Maybe if we would sell these solutions, then how much we should price them.
Yeah, that might have more to do with a startup having to do with studying for exams.
Alrighty, I'm gonna pause the recording now.